Hello, my name is Eduard Kamburjan, and I'm going to talk about variability modules for Java-like languages with its joint work with Ferruccio Damiani, Reiner Hähnle, Lienhardt, and Luca Paolini. The problem we're concerned with in this work is how to handle multiple variants of one product line in a bigger overall system. As an example, let's look at railway systems. So in railways you have signals which are standing on the side of the road, and you can have a simple variability model for them. For example, a signal is either a main signal, where a train has to stop, or it's a pre-signal which announces that a main signal is following. Similarly, a signal can either be a form signal, where the physical form of the signal transmits the information to the train driver, or it's a light signal, where there are several colored bulbs and the color pattern transmits the information to the train driver. And you can have a very simple variability model for this kind of signals. Now let's talk about railway stations. So this is a railway station, or at least the entry to one, so here's a switch. But now we have four different signals. So we have two form signals here and two light signals here. Similarly, we have the main signals and the pre-signals. So what are we going to do exactly with the variability model that I showed you on the slide before? So we want to reuse it, but we cannot just generate one variant of it, because we need to have four different variants, which must be connected to each other inside of one railway station. So there are three challenges that arise if you want to do this. First of all, the multiple variants must not only coexist, they must also be interoperable, which means that they must be encapsulated, so we don't mix up the different variants, but they also need to share common code, so you don't blow up the system in size more than necessary. And finally, you need to have a dependency mechanisms, because the variants may reference each other and you need to keep track of what variant is used in what place. These dependencies must also be checkable, so I must be able to keep track without a big computational effort to keep track of where what variant is used and whether there are possible bugs or mistakes in this usage. And finally, the mechanism must be natural to the user, which means we don't want to introduce a big overhead on top of the modeling and the variability. And the thing that we are going to do is that in a Java-like programming language, we are going to take the module mechanism, which is fairly standard in modeling and programming languages, and put a variability model inside of the module. And then we are going to reuse the dependency and reference mechanism between modules and between their elements to handle dependencies and references between different variants. So we call this integration of variability into modules, variability modules. And next I'm going to introduce them by example. As the basis, we use the ABS language, but you can imagine to use any other object-oriented language with Java-like syntax and modules. Here's a small example. We have a module, which is called M. We have import and export clauses, which declare what elements are exposed to the outside and which elements from other modules I'm able to use. And then we have elements inside of the module. So here we have an interface and a class. The content of these elements is not that important, except there must be some kind of reference to other elements, for example, via types, or here in the new expression. So modules normally serve as encapsulated scopes. So they're encapsulated because elements inside the module are hidden from the outside unless they're explicitly exported. And they're scopes in the sense that they're name scopes. So I can have multiple elements with the same name as long as they are in different modules. For example, I can have the interface I one time in module M and then one time in module M2. And now if I'm in a module where I'm able to use both of them, then I must make sure that I reference the correct one, and this is done with qualified references. So reference is either unqualified, where I just use the name of the element, or it's qualified, where I prefix it with the module. So here I use the module M and the element I from M, and here I use element I from M2. Variability in ABS is based on delta-oriented programming. So delta is just a set of modification of classes and interfaces or other elements, so I can add and remove classes, or I can modify an existing class and change, for example, its fields. The feature model is restricted by some kind of feature model, and we just assume a propositional logic formula here, and similarly each delta is activated by a propositional logic formula for features. So if I give you a set of features, I can evaluate whether it fits the feature model or not, and I can check which delta I have to apply. So if I have just some set of features, I call it a configuration, but if the set of features is adhering to the feature model of the product line that I'm talking about, then it's called a product. And here's an example. So this is not a variability module, just how to give you an idea of the syntax. I have features, so this is part of the signals. I have light signals, form signals, and features for them. I just say that I have either light or a form signal, and then here the delta says that it adds a class bulb, because we need to talk about bulbs when we have light signals, and then it modifies the class csig to correctly use bulbs. Then here we associate the delta L delta with the feature light. So now a variability module is a module where the variability model is local to its elements. So here you can see I need to prefix everything with the module, because I need to say where I added or what exactly I'm modifying. I don't need to do this with variability modules. So we have now some restrictions. So obviously each delta can only modify elements from its own module, and two VMs cannot share features. So if I have a feature, it's also local to one of the modules. And if I want to share code between different variants of one module, I must annotate it explicitly with the unique modifier, which says that I do not want to have this copied over. Now, for the dependencies and references, every time I reference something inside the variability module which is not unique, I must reference the element together with a product. So here's an example. Here I declare product P, which contains the feature F2, and here I now create three different class instances of C from three different variants, one with F1, one with product P, and we allow also expressions over features. So here I create C from the variant with F1 and F2. So here's an example on how we do this for the railway signals. So here in the beginning, I'm going to show you only the left part here, so form light signals. We have the usual module header, so we export some of our elements. We have the feature model from before, and we declare product, which says that our light signal contains the feature light. Then the core part, so this is the code which is always existing. We have a unique interface which is shared among all the variants, which is called interface signal, and we have here a reference to itself. And then we have a class which is empty and not unique. And now we have the delta from before, so we add a bulb and then we modify the class to create new bulbs. Note that here we don't need to talk about modules anymore, right? Because we can only modify our own module anyway. And then we have more deltas, and later here we have the same association between deltas and features. Now, how do we use this? We can also use this, for example, in other variability modules. So let's say that our railway stations are also a product line. So we have the same module, again a module, we have import and export clauses, and we have two features, whether it's a modern interlocking system, modern railway station or not. Now, because we cannot share features, we somehow need to communicate the choice of the features in one module to the choice of features in another one. And we do so by having more complex product declarations. So we call this open products, where we say that we have a product for a different module. So we define switches here, and we say that if we are in a modern interlocking system, then PS refers to the product containing only the features electric, and if modern is not selected, then it refers to the product which only contains the feature mechanic, where mechanic and electric are features of the switches product line. And now later, we can do two things. So here we create two different signals. We create one light signal, we create one form signal. And note that we do not have to specify the variant for the interface, because the interface is unique, so there will be only one of them anyway. This means that this method call here will work, because it expects an interface signal and it gets one. Right? And it doesn't need to take care of what exactly, because as I said, there's only one. And now here when we create switches, we just say create a switch using this open product, and what exactly we are going to select depends on our own feature selection. So now that we have our variability modules, how do we generate non-variable code out of them? So how do we flatten the program with variability modules into one without variability modules, so that we can perform further compilation steps on a program without dealing with variability anymore? So what we do is we make copies for each needed variant of the variability module, apply the deltas, and update the references. What we do is we go through our program until we hit variability module M, reference to 1, for some element inside of it annotated with product, and then we check, do we already have a copy? And then we go to the next step. But if we don't have one, then we make this copy of M. Then we delete all the unique elements, because we only need one copy of them. Then we import everything from the original copy and apply the deltas according to the chosen product on the copy. So the delta application is a syntactic operation and is exactly as in any other delta-oriented approach as well, except that it's local to this module. So there's no modification needed here. Then we go back to the original reference and replace the variable reference annotated with a product with a qualified name. So replace it with the qualification of the new copy of the module. And then we go into the import clause of the dependent module, so the one containing the reference, and adapt its import clause. And we do this until we have removed all variability references. This obviously terminates because there are only finitely many products and finitely many modules. So at some point we have just generated all the variants, then we can just update all the references. But if a variant is not needed, it will not be generated by this algorithm. Then, once we have removed all the references, we go to the original copies of the variability modules and delete all non-unique elements. So in the end, we have one copy M, which contains only the unique elements. And for each needed variant, we have another copy which contains everything needed except the unique elements. And then we also remove all the product declarations and all the deltas and all the unique annotations. So this is the flattening of the example I have shown you before. We have one module signals which contains only the previously unique interface. And the interface is still unique in the sense that there's only one copy, there's still only one interface signal. And then we have, for each needed variant, here signals light and signals form, one module, and here we import everything from our original copy. We have adapted the export clause, and now we have here the bulb and the variant of the signal which creates new bulbs. And then we have a second module which looks the same except without bulbs for the form signal. And in the place where we have referenced them, we have replaced them, the reference with products, with a qualified module. Note again that the interface doesn't need this operation, right? Because there's only one of them, and we don't need to add a qualified name here because it's still in the same module. So the name of the module with the unique elements does not change. Finally, this one will still type check. So does this always work? And well, it works most of the time, but you need to restrict what exactly you're doing. And this is formulated as the principle of encapsulated variability, which I have given informally before, but what it says is if a module depends on an element from a variable module, then this element must be unique, or I must specify the variant. And inside of a module, each unique element can only depend on other unique elements, or on non-unique elements with a specified variant. So essentially, we are handling the unique elements as an own module inside of the overall module. And finally, we need also to ensure that a delta can only modify non-unique classes, and this altogether is the principle of encapsulated variability. Right. So if I have dependencies, they must make sure that they use variability correctly, have no dangling references afterwards. And then we have a theorem which is a lot more formal in the paper, which says that if a program adheres to the PEV, so if all its checks succeeds and all the delta applications in each variability module succeed, which means I don't remove a class which does not exist, then flattening succeeds, so I end up with a program without variability. Here are two examples of how this can go wrong. So here we have one variability module M with a class D inside, which is not unique, and we have a module N, which creates an instance of D. Now we can have multiple Ds, so if we just look at this, it's not clear which variant we have. So we may have 10 different Ds, but just looking at this, it's not clear which one we are going to use. So if we would just naively flatten everything, we would never update this reference, and it would not be clear which module needs to be prefixed, which one is intended by the programmer. So this would lead to a type error. Similarly, we can have the same situation inside of a module. So here we have a unique interface and a unique class, and the unique class creates a new D instance. Now we have at least two different Ds, so the original one, and here we have a modified one where the delta which continues here. So which one do I create, right? Because they end up in different modules, so I need somehow to annotate here which of the different variants I need to use. So these two examples violate the PEV, so our implementation would reject them. Now for some final discussion and our evaluation. As mentioned, there is an implementation available, which you can check out at GitHub, and there's also a link to a precompiled version. We want to stress that the framework and the PEV are not specific for ABS. Everything you need is a module mechanism with import and export clauses, which encapsulates namespaces, and a notion of reference between the elements inside of this module. Interoperability was originally posed as a challenge case at SPLC 2018, and they had a further approach to interoperability, but we think that this one is far more usable because it's easy to keep track of the references, and especially because it does not introduce new concepts except variability itself. So we reuse the mechanism of modules, we reuse the mechanism of references, we do not introduce new scopes, for example, so we do not break the encapsulation by allowing deltas to perform actions on elements which are not exported, which was necessary before. And there are some things which I have not discussed here, which you can read up in the paper. So everything I have talked about has a formal semantics. I have not talked about product declarations in detail, and not about the exact handling of the import and export clauses, but it's fully formalized in the article. For the evaluation, we have looked at 3 case studies and compared variability modules to prior approaches. So the first approach was to use an external toolchain to mimic interoperability. So the ISCO web portal was using ABS and its variability module for certain parts of the web server. And they used an external toolchain to essentially do what the variability modules are doing as well, except that because they used an external toolchain, it was harder to keep track of the references and was not integrated on the language, but has to be done completely on top of it. And we could re-implement it completely using variability modules. We looked also at the ABS model of railway operations, where we refactored the infrastructure model using variability modules. It was done using traits before and inheritance and object orientation, which had the downside that we could only handle variability inside of one class, while variability modules can handle variability in different classes. And also it has the disadvantage that there were implicit constraints, so certain traits could not be used together, which can be made explicit in the feature model using variability modules. And also we saved around 1/4 of the lines of code for the remodeled infrastructure modeling. And finally, we looked at what would have to be done if you would just use standard product lines. So we looked at our weak memory model in ABS, which is the variability of the communication between a CPU and memory, and looked at what would happen if I would have 4 CPUs with 4 different memory models. Or we just copied everything over 4 times and then manually refactored the common part. So this obviously does not scale because you blow up your feature model as well. So now you have like a copy of each feature for each of the CPUs. Also, it's very wasteful in terms of lines of code. So using variability module saved us around 2/3 of line, even with manual refactoring. So as a conclusion, we introduced modules as a unit of variability and used their encapsulation to make variants interoperable by also reusing the reference mechanism of an object-oriented language. And what we're looking at right now is family-based type checking, so we only type check before flattening and not after.